Hello, I'm Daniel Rabel, and I work for the NASA John Glenn Research Center in Cleveland, Ohio, in space communications and navigation. And I'd like to take a few minutes here to talk to you about some of the communication challenges and some of the engineering solutions that were devised for the upcoming Mars mission. So I have some information I'd like to share with you here, and I can pull that up on my screen now. But just to give you an overall context for what we're aiming to do here is add to a story that's been going on for a few decades in the solar system, which is at any given time, we typically have about 100 spacecraft at different points throughout the solar system performing experiments and making observations. And that's an amazing fact because when you think about a century ago, we had never visited any of these other worlds. And now each time we go out to another planet, we're adding yet another chapter to that story and getting more information from that particular mission. And so we're about to add yet another chapter onto that with our Perseverance mission. And so Mars is the destination for Perseverance. And going to Mars is a very interesting endeavor. It takes Earth 1 year to orbit around the sun. And Mars, the next planet out in the solar system, it takes roughly 2 years. So we get an opportunity once every 2 years when Mars and Earth remain together at one side of the sun. And we launch in a window that's approximately 2 to 3 weeks wide. So we have to hit that launch window and get our spacecraft on a spiral trajectory from Earth's orbit out to Mars orbit. We call that a Hohmann transfer. That's the green line that you see right here in the graph. We have to accelerate very fast. So we need a large rocket to do that. This is a ULA rocket that we used. We have to accelerate up to a speed of about 95,000 kilometers per hour in order to catch the planet. That trip takes a duration of about 7 months long. And during the course of that spiral transit out to Mars, we're continually communicating with the spacecraft and making observations on its trajectory, both in terms of its speed and trying to make small course corrections based upon that speed. Try to take measurements down to very fine resolutions. We're talking about 0.1 millimeter per second velocities that we're able to resolve through our navigational systems. And also, when we get to the planet, we have to be at a very critical angle for entry, descent, and landing. And we're able to measure those angles again through our communication systems to make sure that we're at precisely the right angle to enter the upper atmosphere of the planet. And we can measure that down to matters of about 2.5 nanoradians of angle, which would translate to hitting a targeted landing zone of about 1 kilometer in size. And we're able to do that all back from Earth, from our communications and navigational systems. So that brings us to now, that critical part of that transit, which is the entry, descent, and landing phase for Perseverance. And this is a very complicated series of sequenced events. So you can see that there's multiple parts of the spacecraft that are going to detach and deploy from a parachute to a sky crane and a tether, lowering the rover down to the surface ultimately. This is similar to what was done with the earlier Curiosity rover, but there's one interesting difference, and that we've built some autonomy into the system known as terrain relative navigation, or TRN, where the spacecraft during entry, descent, and landing is going to be capturing images of the surface to try to fine tune that descent in order to hit our ultimate landing zone, known as Jezero Crater, which is part of an ancient Martian lake. And so it is going to have control over the final part of the descent in case it sees some rocks or things on the surface that it needs to correct for. And really, this is enabling us to hit this particular landing zone, something that we weren't able to do with previous missions. So each part of the spacecraft, as you can see on the left here, is instrumented and has several antennas on board, so that you can think of it like a demonstration of a new technology. We can telemeter all of that information back to Earth to see how well this TRN system performed during entry, descent, and finally landing. Now, once Perseverance is down on the surface, it won't be alone. We have sent a lot of hardware to Mars, in fact, more than any other planet. There are several rovers, and Curiosity is still there as well. And we have several orbiters who have been there for a few years. And this is going to be important. We're going to try to take advantage of this as a communications network once we arrive. As well, going to the future, we have several more surface assets as well as orbiters planned for the Mars exploration program. Now, the rover itself, known as Perseverance, looks very similar and with locomotion wise as well with the original Curiosity rover, but it has a whole new host of instrumentation on board. And like I mentioned, this will be landing in a crater that is an ancient riverbed, looking for signs of microbiological organisms, gathering rocks and soil, and trying to identify things that we can utilize for future human exploration. It certainly has a few high definition cameras on board, and that, together with the other scientific instrumentation, is going to generate a lot of data to ultimately transmit back to Earth. And that's where our communications and navigation really needs to come in and try to make that possible. There's a lot of challenges working against that goal of getting all the information from the surface of the Martian planet back to Earth. Like I mentioned, Mars is very far away. It takes us 7 months to get there. So it's so far away, in fact, that the radio signals themselves can take several minutes to transit between Mars and Earth, typically on the range of 5 to 20 minutes, depending upon the particular placement of Earth relative to Mars at that point of the year. Remember, that's varying because we're in 2 different orbits, a 1-year orbit for Earth and a 2-year orbit for Mars. So we can't, ask a question of the rover and get an instantaneous response. We can send a command or ask a question, and then takes up to 20 minutes for that to get to the rover, and then perhaps 20 minutes back. So conversation is very slow that way. It's a very harsh environment. It can get down to minus 90 degrees centigrade at night, which is the coldest temperature ever recorded down in Antarctica here on Earth. There's also huge, large-scale dust storms and radiation storms. You can see just in a few weeks, these are pictures of Mars in the lower right-hand corner here of how a dust storm can envelop the entire planet. And that can knock out our communication systems. The rover itself, although fairly large as rovers go, is still very limited in the available power and the available computing processing power that it has. I believe after this, my colleague Lauren Clayman is going to talk to you about the radioisotope thermal generation system. And our communication systems are just one of many different payloads on the rover competing for that valuable power from that RTG. And so we're limited in how much energy that we can have to transmit the signals back towards Earth. Now, there are planned outages as well. Certainly Mars is in orbit, Earth is in orbit. We're both rotating as planets, and the rover's driving around. So everything's in motion, and we can kind of pre-plan that out and know when we'll be able to establish a communication link to the planet. But there's also unplanned outages. We can have, obviously, weather effects here at Earth, in the way of thunderstorms that can knock out communications. We also have what we call space weather, which would be some of the radiation storms coming from our sun that can impede communications. So a lot of things working against us in trying to work these signals back towards Earth. So on the rover, where those signals start is we have 3 options, 3 different antenna systems on board Perseverance on the top deck. The primary way of communicating is a small antenna known as an ultra high frequency antenna, or UHF, and that will transmit from the surface of the planet up to one of 3 available orbiters, the Mars Reconnaissance Orbiter and MAVEN, as well as the European orbiter, the Trace Gas Orbiter, TGO. And so those are already there, and they'll come overhead about once a day for about 8 minutes over the rover. And when they're overhead, we'll be able to transmit at a rate of 2 megabits per second. From that UHF antenna. And this works out well because those orbiters, as you can see in the picture here, they have very large solar panels. So they have a lot of power. And 2 from the pictures, you can see they all have large antennas on board. So they can ingest that 2 megabits per second from the rover and boost up the signal for the long haul path back towards Earth. And so the majority of the data will be transmitted in that fashion. Now, in addition to that system, there's 2 other systems at a different frequency called X-band. There's a high gain antenna and a low gain antenna. The high gain antenna, you can see on the picture on the inset here, is a steerable antenna. Now, it's a very low data rate. It's down to about 160 to 500 bits per second. But it's steerable, and it will be able to communicate with Earth directly rather than relaying the signal through one of those orbiters for a fraction, of time a day. And so this is how we'll be sending commands every morning to the rover. So very low data rate, but very important information. We wouldn't be sending pictures and video back and forth on this link. But this would be more for our commanding information and critical telemetry information. And the nice thing about it being steered is that we can have the rover in whatever pose it needs to be in for its mission operations and independently steer the beam around, so we don't have to worry about what position the rover is in to communicate. And then finally, there's a low gain X-band system. Again, very low data rate, just as a backup option to give us some flexibility in case we had a problem and perhaps the rover's in safe mode and we're trying to recover from some event, unforeseen event, like a radiation storm or that. So we have 3 different channels here and different frequencies that we communicate in those channels. And you can imagine there's a lot of science and engineering that goes behind that. And NASA is certainly full of a lot of science and engineers to build the systems to allow this to happen. But I also wanted to take just a minute here to mention, so these channels operate at different frequencies, the same way that your cell phone has a certain frequency and your wireless internet, your router at home has a certain frequency. And just like all of those consumer grade products in space, NASA has to get a allocation to use that frequency. We have to get an authorization for each and every one of our spacecraft, and each and every one of our spacecraft may need multiple channels. So there's an entire team at NASA made up of folks that have a bit of a legal background and a management background that work with our international partners all year to make sure that all of our spacecraft are allocated the right channels that they need, the right frequencies that they need in order to communicate to and from Earth. And that's an ongoing effort. It takes a few years prior to each of these missions to get those spectrum allocations. And it's something that a lot of people don't know about. So they're the unsung heroes of making all this work. And I just wanted to make the point that it takes, a whole lot of different types of people to pull these systems together, from the hardware and the software, the science and the engineering, but also the policy and the management of that. And the spectrum allocation is a perfect example of a critical piece that you need to make these systems work. One very new feature with this rover of other rovers is the Mars helicopter, known as Ingenuity. So there will be the first powered flight demonstration on another planet using Ingenuity, which will deploy from the Perseverance rover. And what Ingenuity is going to add from a mission capability standpoint is we'll be able to reach things like plateaus that the rover won't be able to climb, and go to ranges where the rover will not be able to get to, and get increased resolution and imagery from those particular locations. Now, from a communication standpoint, this creates a small network right down on the surface, because all of that imagery captured by Ingenuity will have to be relayed through the rover itself, and then up to the orbiter, and then back towards Earth. So we've basically built our own local Mars communication network between each of those elements in order to get the data ultimately from the helicopter demonstration and telemetered back to Earth. So very interesting and exciting demonstration that'll be deployed from the rover itself. Now, Perseverance as well is going to have several cameras on board, and we're greatly looking forward to the enormous amount of data that will be returned from those cameras. So as that starts to roll in over the next few weeks, please check out the Perseverance rover website for downloads of that information. Here's an example of just such a picture that was downlinked through Curiosity. Now, these images are very large. Some of them can even be gigabits large in file size. So it can take a few days and sometimes even a few weeks to download something like a panoramic mosaic like you see in this very image due to those data rates because of the long distances. But they will be adding that to the repository over time, and we're very much looking forward to seeing the kinds of imagery that Perseverance is going to give us on top of Curiosity. So back here at Earth, and that's the last part of communicating across this Mars relay network, are deep space network antennas known as the DSN. So the DSN features the very largest antennas that NASA operates. They have the most sensitive receivers on board. They also have the most powerful transmitters inside. So when we need to send the command and control information every morning to the rover so that it knows what operations it should do that day, we're going to also use these antennas as our transmitters. During that cruise phase, that 7-month cruise phase, these are the antennas that also provided all those navigational, we call them the radiometric analysis to make sure that we're at the right trajectory, the right speed, and the right angle. And to do so, we have to drive these systems with the best algorithms and the most stable timing, with atomic clocks and such, in order to provide that navigation to the rover from Earth during cruise phase. And typically at any given time, we have about 30 different craft in deep space, so about 100 across the solar system, about 30 in deep space that the DSN is talking to on a daily basis. So the DSN is a network, and for network, deep space network, and there are 3 facilities for the DSN spread across the planet. We have one in Goldstone, California, Madrid, Spain, and Canberra, Australia. And the reason that these very sites are picked is because they're roughly 120 degrees apart from each other on the Earth. And so whichever way the Earth is rotated, you were able to use one or sometimes even 2 of these ground terminal facilities to communicate with one of the deep space craft, such as Perseverance. And so some of the signal will go to one of the antennas, and the Earth is slowly rotating. So then you have to hand off to perhaps another one of the antennas to get the rest of the message or download the rest of the image. And then ultimately, those pieces of the signal need put together at a central operations facility, which resides out in Pasadena, California, out at the Jet Propulsion Laboratory, the JPL Space Flight Operations Facility. And if you're ever out there, you can get a public tour of that facility. It's been in operations now 24/7 for over 40 years, communicating with all of our deep space craft. And of course, we're in a very interesting time, just like you and I are struggling to figure out how to get through our day to day due to COVID-19. The Space Operations Facility is doing the same. And in fact, in this past year, it was the date of March 20th. That was the first day for the NASA Curiosity rover to be successfully operated from the operations team who was telecommuting from home. And of course, we've had to continue this mode of operation for some time, but it's pretty amazing the technological successes of figuring out how to lay in secure channels where you're able to operate a spacecraft in deep space on the surface of another planet from your house due to the constraints of a worldwide pandemic. So big feather in JPL's cap for figuring that out. Now you can watch live the operations of what those operators are doing anytime that you like. This is up 24/7. If you go to the DSN Now website, and I just took a screenshot of it here for you to take a look at. This will show you the three different facilities, and there's several antennas at each, and it'll annotate which spacecraft we're talking to at that instantaneous time. So right now on the screen at the very bottom in the center, you can see that the Canberra site, which was in the center, the 34-meter dish, was actually talking to Voyager 2 at that time that I took that screenshot. And if you'd like to learn more about the mission or the communications system, you can click in the bottom right and find things like how far the mission is away, what's the data rate, what's the latency and time. Right now, I think it's selected Mars Odyssey, and there was a 42.94 minute time delay talking to it. So really neat website. I encourage you to check that out, especially now, watching us start to bring Perseverance online, and it'll appear in here daily as we start to talk to it. And so, like I mentioned, there will be a lot more hardware going out towards Mars. These are the robotic precursor missions where we can find out what type of resources are available to us to enable human exploration. And we have to continue to do these first to learn more about ourselves and our solar system, where we are and where we're going. And we need a lot of help to do this. And there are many ways that you, the public, can participate in this. We have small business opportunities where, the algorithms and the software and even the hardware that we use on these spacecraft can get developed from a small business interested in doing so. We have larger contractual mechanisms for procurement, but the one I really wanted to focus on is our academic collaborations. We are very fortunate that every year we have a large segment of interns coming to join us. And in fact, right now, this very second, we're reviewing applications for the summer internship. I believe they're open for another couple weeks here. And so if you know someone or you yourself are interested in helping us accomplish these missions, by all means, consider interning with us. And that goes from high school to undergraduate to the graduate level to the postdoctoral level, and even faculty fellowships. And like I said, this is something that is crucial to our success, getting in young, bright people with new ideas and help and getting their feedback on what we're trying to do and getting their help trying to get there. Again, I'm from the Glenn Research Center, which is in Cleveland, Ohio, in the Great Lakes region, but we have facilities all over the country. And so if you're not able to travel or you'd like to have something a little closer to home, you can go through the main web portal and basically it's like a job board, find something that you're interested in and put in for it. And we will be most happy to have you aboard our team as we go forward. So I hope that you found this very interesting. Thank you so much for your attention. Also, thank you to the Great Lakes Science Center for helping us get our message out here as we continue to add, again, more chapters to our story in exploring our solar system and beyond.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming.
TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.